Okay, I'm not going to put this in the presenter view because it didn't work last time, and that's real fun. So, welcome to Lab 2, Motion of a Falling Object. First off, the problem we're tasked with today is observing the motion of a falling object and comparing it with similar predicted ones in GlowScript simulations, and seeing how the impact of the drag force affects the force of gravity and constant velocity overall on the object. What does it mean, and the what if question are hypotheticals that we hope our data today can help inform. The principles we're going to be using to solve these questions are gravity near Earth's surface, Fg equals ma, and of course Newton's second law is specifically the position update formula to help us plot our data points over time and see where the actual object is in the y direction as it's falling. The drag force is going to be used to show air resistance in a realistic setting. And yeah, the video is not worked ever, but you're not missing much, I promise you. The actual video is me dropping a cardboard box of tea. Slower than a rock, but not more interesting than a rock. So this shows in the tracker video actually that when compared with the gravity just in a GlowScript simulation of a similar object, a different speed overall in time reaching the bottom, just because gravity isn't the only thing acting on the tracker observation. It actually shows that when placed against a simulation that something else comes into play, and this difference is air resistance. These are the two different GlowScript graphs and the tracker graph coming all together in a single one. The tracker video is much shorter just because it's 30 frames per second, and I enjoy more precise data, so I plotted more points on the simulations, so it makes the tracker end a little earlier, and it shows actually better the exponential drop with air resistance of gravity, of velocity impacting this, and the blue line is actually with air resistance from the simulation, and the orange line is without. You can see the blue line actually slows down over time and is overtaken by the orange. This is because speed drops with gravity being opposed and eventually balanced out by another force. This is the velocity versus time graph showing the actual exponential of the two forces, and then velocity balancing eventually into a constant with an F net equaling 0 because air resistance and gravity have successfully balanced out. Seeing all this data brought together, the drag force, although small in the actual tracker video, shows that the importance of air resistance and that it is not just always negligible and ends up mattering quite a bit, especially when it comes to terminal velocity. With enough time, the air resistance, as we saw in that previous graph, and the force of gravity would leave the object in a constant velocity with a net force of 0, and this is the only way that terminal velocity is reached. And the hypotheticals very much directly relate, is because that velocity versus time graph is what's so valuable, and how we can predict this terminal velocity is because we just have to simply look for where it becomes constant. Once it becomes constant, that's when we've reached it. The what if question of being thrown downwards versus dropped, really the terminal velocity would be eventually the same, as you can see. With the position versus time graph, the gravity actually sped up while the blue graph slowed down. I'm saying these things, but I can show them as well. The blue graph slows down because it's eventually becoming a constant, while the orange is just going to linearly increase over time because there is no, the net force is constantly changing. And so, that is all I have for you today. Thank you so much for listening. Good luck in our test next week. I'll talk to you all later.